You've seen the title of this video then. I would implore you not to just skip to the end for multiple reasons. One, because you probably won't have any idea what the problem is about and therefore won't be able to do it. But also, the journey towards the actual problem here is so much more interesting than the problem itself. There's something wild going on that I'm going to talk about today. And the very mechanical problem that I'm going to give you at the end is not interesting. And it's why one of the reasons I haven't solved it probably is because it's not an interesting thing to solve. I just haven't done it. I have tried though. But the actual problem leading up to this is so much more interesting than the problem itself. So I'd advise that you stick with me and do this. There will be times as well when I ask you to pause the video and maybe have a think about something extra as we go along. I've been thinking about this problem for probably over a year, maybe around I think just over a year is when I first heard about it. On and off I've been thinking about it. I think it's ridiculously interesting. And I haven't quite finished it off, which is the purpose of this video is hopefully someone, and I know there are people who watch these my videos who are a bit more talented than I am. Hopefully someone can finish it off for me instead. So we'll start with a quadratic, and I'm going to say that this quadratic is interesting, and you might be thinking, no, it's not, and you're probably right. It does factorize, and that's kind of interesting because not all quadratics factorize at least so easily. All quadratics do factorize, but this one factorizes very easily. Now, if I just change this sign to a minus, it still factorizes. And if I change this sign to a minus, it still factorizes. And if I change this sign to a minus, it still factorizes. And that is interesting. It factorizes with these two numbers regardless of the ways that I write the signs. There are 4 ways to change these signs around, and it factorizes for all of them. And that is interesting because it is rare to find a quadratic that does that. For example, this one here does factorize with 2 pluses. It still factorizes if you put a minus here, and actually, of course it does, because all you have to do is change these two to a minus, because 2 minuses still multiply to make the same positive they did before, and will add to make a negative to what they did before. So that's kind of obvious that it still does it here. But if you change this sign instead, then it doesn't anymore. And likewise, if you then change this sign, it doesn't anymore either. And so this doesn't do it. Since I did some Googling and I couldn't find anyone talking about quadratics like this, so I thought I'd take the liberty of naming them myself. And I'll call this property A factorization, short for all factorization. It always factorizes. So we'll call quadratics that do this A factorizable. Okay, and maybe the first time you want to pause here is, can you find any more A factorizable quadratics? Can you find any more aside from 5 and 6? So maybe do that. Maybe look for some more. You could also ask yourself any of these questions. Firstly, can you find any more that do it? How many do it? Is there just one? Is the one that I've given you the only one that does it? If it was, I probably wouldn't be making the video. But on a serious note, how many are there? Is it one of those things where they're an infinite number? Or is there something about low numbers that makes it work, and somehow higher numbers won't, and therefore there's a limited number of them? If not, maybe there's a system. If there are an infinite number of them, maybe there's a system you can find to create more. And lastly, and probably the most difficult and open-ended question, can you find anything that intrinsically connects the quadratics that you found together somehow? Is there a thing that they all have, or a tell that they all have that means you can point at and go, yeah, that's why they're doing this? Okay, so I hope you've had some time to think about this. I'm going to flash up 3 of them. These 3 here, I think are the 3 findable quadratics, or A factorizable quadratics, findable by humans. I think these 3. So you might have found these, well done if you did. Something interesting is going on with this one and this one, I think. You can pause the video again if you want to, and think about why I think these 2 are interesting. This quadruple and this quadruple. I think they're interesting because if you just double this one, and then times this one by 4, or 2 squared. You get that one? So double times by 4, or 2 squared. And if you choose to do it by 3 and 3 squared instead, you make this. And it turns out that that's also A factorizable. So that's really interesting. Maybe you could think about if you times by 4 and 4 squared, and 5 and 5 squared. Are they all factorizable? And if they are, can you prove this? Because that would be a system. And then you'd have an infinite number of them that do this. So I think that's all quite cool. What I'm going to do now is I'm going to leave quadratics to the side for a second, and we're going to just do something completely different in maths. We're just going to look at some other completely separate area of maths. I hope as soon as the new screen comes up, you'll immediately go, oh yeah, that's completely different. So here they are. Let's look at some triangles. And I hope everyone watching, I think everyone who watches my videos can work out the hypotenuses and the areas of these triangles. I've actually, for some reason, already given you the hypotenuse of this triangle, but I think, again, people who watch my videos probably know the 3, 4, 5 triangle anyway, so it doesn't make a difference. Anyway, while I've been rambling, you have probably worked out these. We've got hypotenuse 5, area 12, sorry, area 6, 3 times 4 is 12, halved is 6. Hypotenuse 13, 5 times 12 is 60, divided by 2 is 30, and likewise here and here. And I think some of you will have immediately noticed what's happening here. Because 5 and 6, 13 and 30, 10 and 24, if I use those numbers and put them in the right places in the quadratics, I think we get the 3 quadratics that we were just looking at, that A factorize. By the way, these are called Pythagorean triples because all the numbers are integers. That doesn't always happen on right angle triangles, of course. 1, 1 root 2, for instance. So it seems like when you take a Pythagorean triple and put the area on the end and the hypotenuse as the coefficient of x, you make a quadratic that A factorizes. And we haven't seen this one, right? Does this one A factorize? These are all the ones, remember? These are the right numbers, right? But does this one do it? And actually, yeah, it does. You can put it into, of course, this is going to do it because you just change the signs. It's this one that's the big one, right? But of course that one does it as well, and then when you change this, you just change those 2 signs over and you make that. And I don't know about you, but when I first saw this, my mind was pretty blown. And I was like, well, I actually just thought that's just a coincidence. We've just cherry-picked a few good examples. Not sure what that number is doing there. Completely irrelevant. We've just cherry-picked some good examples, and this can't possibly be a thing, right? It can't possibly be a thing. But then you remember that system we found earlier about timesing this by 2, timesing this by 2 squared. And some of you might have proved this in your own time in between pausing the video. But you realize, well, hang on, 3 squared, 2 squared. Where in maths do you times something by something, but then times it by something squared in another time? You do that in scale factors, right? When you multiply across area and length, a scale factor across length is, you square it to get the scale factor across area. So because we're building our quadratics out of a length thing here and an area thing here, if we double the length thing, we quadruple the area thing, right? That's how scale factors work. So there seems to be some evidence here that these 2 things are connected. And then you bring up the database for Pythagorean triples, and you just pick one at random. You work out its area by multiplying these 2 and halving it, and then you shove this into this number and this number into a quadratic, and then you put it in Wolfram Alpha to see whether it factorizes, and then you change the sign. Of course, this factorizes because it's going to be negative of those. The big one is this one. When you change this sign, Wolfram Alpha says it works, and then you do again. Okay, what is going on? Like, what on earth is this? Why would this do this? Why would Pythagorean triples make quadratic? What on earth is going on is my big question. Is this can't be a coincidence. We picked a random quadratic Pythagorean triple from the database, and it just worked. Like, how is this a thing? And there's a few things that could be going on here. There's 2 major questions you need to ask that look fairly similar when you first look at them. Firstly, is every quadratic that A factorizes built out of the hypotenuse and the area of Pythagorean triple? In other words, is every quadratic that factorizes like this, do you need to have the hypotenuse of Pythagorean triple here and the area here? Do you need that? And likewise, is every Pythagorean triple, if you take a Pythagorean triple and build a quadratic out of it, will it definitely A factorize? Those are 2 different questions, and you need to answer both, really, in order to fully understand this question. And this is kind of where I'm going to leave you. I'm going to leave you with these questions. I'm not quite. I've never talked about set theory on this channel properly. Lastly, is this all just a coincidence? Because it could be. Let's bring out some set theory. Now, you'll recognize this as a Venn diagram, but mathematicians like to use Venn diagrams to understand relationships between things. So in this circle, I put all the quadratics that A factorize. And in this circle, I put all the quadratics that are built out of a Pythagorean triple. And what I'm asking is, the ones that we found, so this A factorized, this is the first one we saw, and it's built out of the hypotenuse and area of Pythagorean triple, that belongs here because it's both. And so did this one. What I'm asking is, are there any quadratics that A factorize that do not have the hypotenuse and area of Pythagorean triple here and here? Because they would go there. And are there any, or are there any quadratics that are built out of Pythagorean triples, so the hypotenuse here, area here, that don't A factorize? Because we haven't been able to find any in either case yet. We have found some that are neither. This is neither the hypotenuse and area of Pythagorean triple or A factorizes. This was the first one we saw that didn't. So the picture could look like this, but we haven't found anything that goes here or here. There's another option for our set theory diagram, which is this. Maybe every quadratic that A factorizes is built out of a Pythagorean triple, but there are some Pythagorean triples, or quadratics built out of Pythagorean triples, that don't A factorize. Again, we haven't found any, but maybe this is what the picture actually looks like. Or, in reverse, maybe it looks like this. Maybe any quadratic you build out of Pythagorean triples do A factorize, but not everything that A factorizes is built out of a Pythagorean triple. Again, we haven't found one, but maybe this is what it looks like. Or, finally, last case, maybe these two circles from the Venn diagrams, maybe they're just one circle. Maybe all the quadratics that A factorize and all the quadratics that are built out of Pythagorean triples in this way are one and the same, and we just have this singular circle. Now, this is where I'm going to leave you for real, because I don't know the answer to this question. I know more than I'm letting on, for sure. In fact, I'm not going to present any of the proofs that I have, because I think that's just spoilers for people who want to give this a really good go. What I will say is that I've eliminated 2 of the cases we're currently looking at, and I have incredibly high suspicion which one it actually is out of the 2 that I have remaining. I have an almost complete perfect proof to show which one it is, but there is a massive gap and hole in my proof that I cannot seem to fix up. So I will leave you here with this problem, and I will wish you good luck with it. I hope someone can do it for real, maybe attack it in a different way that I've attacked it that will allow them to solve it for real. I will also say that I know I'm hitchhiking 3 blue 1 brown here, but lots of you might be tempted to write in the comments if you find some kind of complete proof. Please don't. What I would really like to see is someone to make a video. If you don't make videos about maths yet, just make a video. It's really not that hard. Just get out your laptop, record yourself going through the proof, and make a video on it. I think that would be really good. We need more people making and discussing maths, both on YouTube and across the board, really. So yeah, if you do come up with this, please do make a video discussing it. I would love to watch it. And yeah, I'll leave it there. Good luck.